Hi, my name is Pranav, and today I'll be presenting joint work with Maryam Bahrani and Tim Roughgarden on centralization in block building and proposer-builder separation. Now, our work considers two key questions. We first ask whether heterogeneity and sophistication across different validators and how good they are at building blocks inevitably leads to centralization. And second, to what extent proposer-builder separation helps address some of these concerns by reducing the heterogeneity in rewards different validators might receive, and in turn helping preserve decentralization amongst the validator set. To start with, let's consider the basic block building problem that gives rise to this heterogeneity. So anytime a validator is chosen to be the leader for a slot, they're tasked with creating an optimal block out of the pending transactions that propose to the protocol. Now, block space is highly constrained, making this a highly non-trivial problem. Validators can't simply include every transaction they hear about. Instead, they have to run some optimization algorithm to figure out what the best transactions to include are. And now MEV and private mempools makes this problem even harder. Instead of just having to optimize for net transaction fees, now even different orderings of the same transaction might have different values for the block producer depending on how they affect the application layer. And now all the transactions might not even be in the public. There might be different sources of private order flow and private mempools that basically allow some validators to create more optimal blocks than others, and in turn allowing the more sophisticated validators to earn more rewards from building these more optimal blocks. We show how this naturally leads to centralizing forces amongst the validator set, and we give two different explanations for this. At first, we show that validators who are more sophisticated and in turn can expect a higher return from their investment to stake will be incentivized to invest more capital into purchasing stake in equilibria compared to less sophisticated validators who don't earn as much rewards. Second, we'll consider a model where validators are basically reinvesting all of the rewards they earn into purchasing more stake. And we'll show if we consider the long-run dynamics of how this process might play out, we can expect stake to quickly centralize amongst the most sophisticated validators compared to the least sophisticated validators when there's large degrees of heterogeneity in the validator set in terms of their sophistication. So to start with, let's consider a basic model to answer these two questions, or to analyze these two different settings. And so we'll consider a finite set I of n different block producers, who we'll refer to as BPs. And we can kind of think of block producers and validators as interchangeable for this part of the talk. And so we'll say that each BPI has an associated reward multiple mu I, where mu I will basically capture how sophisticated the validator is, with the higher mu corresponding to a higher sophistication. And we'll say that each reward has kind of a base block reward of R that any validator gets by just participating in the protocol whenever they're chosen to be a leader. And we'll say that when block producer I is selected, they actually win mu I times R. And so as an example, if there's a block producer with mu I equals 2, this means it might be able to extract much more than just the basic block reward by having some optimization algorithm that optimizes for fees, or maybe they are good at extracting MEV or anything along these lines, compared to a block producer who might just have mu I equals 1, and then they simply just collect the basic block reward without doing anything extra. And so then we'll denote block producer's I stake by pi I, and the vector of all stakes by just pi. And then we'll also define this function x, which will capture the fraction of the total stake that block producer I controls. So it'll simply be block producer I's stake, pi I, over the sum of all the stakes controlled by any block producers. And then finally, we'll also assume that the block producers are sorted in decreasing order of sophistication. So block producer 1 will have the highest mu, and block producer n will have the lowest mu. So we start by considering a static analysis of how much block producers might invest in equilibria in a single shot game. So we'll assume a fixed per unit cost of staking C. You can think of this as capturing, for example, the interest rate that block producers might be able to earn on their capital if they kind of put it towards other purposes instead of purchasing stake. And using this, we can then define the utility of BPI for investing pi I into stake when all the other stakers are investing this pi minus I amount of stake by simply mu I times R, which again is how much a block producer will earn if they're selected to be the leader for a slot, times this value xi of all the pi's. And so again, this xi represents the fraction of stake block producer I controls. And so we're implicitly assuming some type of risk neutrality and that the protocol is using some type of leader election where a block producer is kind of selected to be leader based on the proportion of stake that they control. And so mu I times R times xi is basically the expected reward a validator might earn in any given slot. And then we subtract out the c times pi I to represent how much an effective validator has to pay to acquire this much stake. So given this, we'll then define an equilibrium staking distribution, pi hat, where pi hat I will basically be block producer I's best response to all of the other block producers basically investing this pi hat minus I. And one thing to note is that our function u here is actually strictly concave because of the structure of x. And so that means that we'll actually be able to find a unique pure Nash equilibrium for this game. And so that's what we'll be looking to characterize based off these different mu i's in C. And so to do this, we'll first define this notion of a block producer set being gamma k competitive, where a block producer set is gamma k competitive if mu k plus 1 is at least gamma times mu 1. So what this means is that a block producer set is gamma k competitive if there are at least k block producers that are going to be earning at least a gamma fraction of the rewards that the most sophisticated block producer is whenever they're chosen to be leader. And so then we have this theorem that characterizes the maximum market share, where if we fix a base reward R and a staking cost C, then for any gamma k competitive block producer set, we can bound the maximum market share that any block producer might invest by this amount 1 minus gamma times k over k plus gamma. And so for some concrete numbers to give intuition of what this might look like, if we set gamma equals to 0.9 and k equals to 10, so that corresponds to we have at least 10 block producers earning 90% of what the most sophisticated block producer might earn. This tells us that we might expect that no block producer would invest more than would control more than 17.5% of the total stake at equilibria. To get some further insight into what this looks like, we have a plot showing our bound for different values of gamma and k. And so we can see, as might be intuitive, that when gamma is quite small, that the most dominant, the most sophisticated validator might control an overwhelming fraction of the total stake. But as gamma gets closer and closer to 1, then we start increasing k, corresponding to a more competitive block producer set, that we can really limit how much we might expect the maximum, how much we might expect the basically block producer that's the most sophisticated to control. And the dotted line here corresponds to the 33% line, which is basically the amount that if any one block producer or validator got over in terms of the amount of stake they control, then the safety and liveliness properties of the underlying consensus protocol might start to be violated. Now we move to a dynamic analysis where we now consider a model where block producers are continuously reinvesting the rewards they earn from block production back into purchasing more stake. And so in particular, we're not going to be doing any game theoretic modeling. We're not going to assume that block producers are making choices about investing more into stake or less into stake. Block producers won't be withdrawing their stake if they end up having a very small fraction of the market share. Instead, block producers will simply add to their stake if they are chosen to be leader for a slot and otherwise leave their stake untouched. And so we'll now basically use this notion of epsilon centralization to talk about whether the stake is accumulated to a specific validator. And so we'll say the stake is epsilon centralized if there is some block producer I where the fraction of the stake block producer I controls is at least 1 minus epsilon. And from prior work, we know that if there is some degree of heterogeneity in the block producer set, then we can basically always expect that the stake will eventually become epsilon centralized no matter what. But what we try to do is give concrete bounds on how long we might expect this to take based on the degree of heterogeneity across different validators. And so to do this, we'll introduce a bit more notation to characterize this dependence on time. And so we'll say the stake of BPI at time t is this pi I minus I comma t. And then we'll define the staking process for different times as follows. We'll now also just modify our definition of x a bit to also take into account time. We'll define xit as the fraction of stake that block producer I controls at time t. So pi it is how much stake block producer I has at time t, and then the sum of the pi jts is how the total amount of stake controlled by all the block producers at time t. And so again, we'll be assuming that the protocol is using some leader election that picks block producers proportional to how much stake they control. So xit will also be the probability that block producer I is chosen to be the leader in slot t. And so then we'll have our update rule for the stake as follows. We'll say that if block producer I star is chosen to be the leader in a slot, then the stakes evolve according to basically having pi I comma t plus 1 is going to equal pi it plus mu I times r if I equals I star. So that is if I is chosen to be the leader for the slot, then we'll update their stake for the next slot by the amount they would have won in that prior slot. And otherwise, the block producer I, for all other block producers, their stake will remain untouched. So again, we only update a block producer's stake whenever they're chosen to be a leader, and otherwise their stake remains fixed. There's no kind of game theoretic thing where certain block producers are investing or withdrawing over time that's separate from this. And so our main result here are upper and lower bounds on the number of blocks you expect for epsilon centralization to happen. And so for the purposes of this talk, we leave out the lower bound. You can check out the papers if you want to see those details. It turns out the lower bound looks extremely similar to this, but just some high-level takeaways. To bound the probability with which this bound holds, we simply just need the ratio of the basically per round rewards to the total amounts of stake. And so pi minus 1 will be the total stake that every block producer controls apart from block producer 1, where pi 1 is just the amount of stake block producer 1 starts with. And so we also need this parameter rho, that's the ratio of these two amounts. And while this bound might look very messy, in particular the thing to focus on is this term mu1 over mu1 minus mu2 and mu2 over mu1 minus mu2 in the exponents. And this is really where our heterogeneity of the block producer set really comes into play, where when mu1 and mu2 are very close, then this bound gets very, very large. As mu1 minus mu2 gets very large, then this bound becomes weaker and weaker. And so this kind of shows a strong dependence on how long we might take epsilon centralization to occur based on kind of how heterogeneous the block producer set is. And so really the key takeaway from both of these rewards should just be that heterogeneity in rewards amongst validators can be a strong centralizing force. But from what we've seen, even modest reductions in this heterogeneity can go a long way towards decreasing the centralizing forces. Of kind of in the first model, when we get gamma closer and closer to 1, we can really start to limit the maximum market share any validator might control. And kind of in this previous dynamic model, even kind of small reductions in this mu1 minus mu2 can have kind of exponential effects on how many blocks you might expect to take for the stake to become centralized. And so it can be really important to try to limit this heterogeneity in rewards across these different validators. And we'll be showing that proposer-builder separation does just this. And so the key idea here is that the role of block building can be separated from participating in consensus and proposing blocks, where while there might be a few different sources of how validators can earn different rewards, the one we'll focus on for this paper is kind of just the pure process of block building, where the algorithmic difficulties from building optimal blocks, just having sources of order flow, as we kind of described it before, kind of the causes of heterogeneity in rewards these can cause, proposer-builder separation can help with, at least. And so the idea is we'll basically have an auction in every slot between specialized builders, where they will compete for having their block be proposed. And so what this does is it allows validators of different sophistications to earn an equal amount of rewards. The idea being that running this auction doesn't require too much particular skill, as long as we'll also consider an idealized model here. So as long as the auction is run fairly simply, we should expect that in expectation, these different validators should earn an equal amount of rewards. The main concern that we'll focus on in this work is that what if a validator is still privately block building on the side, and we'll ask whether they can make significantly more rewards from doing this compared to validators who simply just run the auction naively. And we'll basically show that even if validators are doing this private block building, they can't earn too much more in rewards if there is sufficiently high, block builder competition. And so just to get some, just to see how proposer builder separation works in practice, and the idealized model we're considering here. So we'll still basically consider there's this mempool of transactions. There's some set of builders who will each make their own blocks. These builders will then submit bids to the proposer who's chosen for a slot, where the proposer basically then can just hear these different bids and just choose the highest one. And so this is a very simple first price auction. We consider a idealized model here where we're not going to get into details of whether there's a trusted relay or how timing games might affect this. We assume that the proposer can just simply hear bids from all the builders and then just pick the highest one, and they get that reward. And so for a more concrete model of how we're going to analyze PBS, we'll assume there's a set Y of k specialized block builders, where each of these builders Y will have some value Ry for their block to be proposed. And we'll assume in some sense that each of these builders is equally sophisticated. So we'll assume that each of these Rys is an IIE draw from the same distribution, dy. And then we'll also basically assume that each proposer I can optionally build their own block with value Ri. And we'll say this value Ri is drawn from distribution di, but we also assume that the distribution di is in fact dominated by dy. The idea here being that we're going to assume that the proposer is at best equally competitive to the specialized block builder at building blocks. And so for just some more concrete intuition of what this means, basically the probability that any proposer might build a block that's greater than some value x is going to be less than the probability that, or going to be at most the probability that any of the builders would build a block with value x, at least x. And so we'll assume then the proposers follow this utility maximizing strategy, where they'll accept blocks from all the builders, and then we can let B star denote the block with the highest of these bids, which we'll also note by this lowercase b star. And then we can assume that the proposer will privately construct their own block B, where they get this reward Ri from their distribution Di. And then they have a very simple strategy. If the bid they got is higher than the reward they got from building their own block, they'll simply propose this block B star they heard about and collect the reward B star. Or otherwise, if Ri ends up being higher than the highest bid they heard, then they'll propose their own block and they'll get reward Ri. So this basically means that the proposer gets the maximum of these rewards B star and Ri. And now the question we ask is, if every proposer follows a strategy, what is the maximum expected reward one proposer will earn compared to another? So the two extremes here is that you might have one proposer who is effectively never privately block building. And so you can think of this as corresponding to a distribution Di, just that's a point mass at 0. And so this block producer is just only collecting the expected rewards from running the auction. Whereas there might be another builder who's maximally sophisticated in our model, and which corresponds to being equal to the block builders and how good they are building a block. And so their distribution Di is going to be equal to Dy, and they'll effectively be getting an extra draw from this distribution, which might affect how much rewards they get at the margin. And so we'll be looking to kind of exactly bound how much more the strategy might earn such a proposer. And so our main theorem in this section is exactly doing that. And so if we let there be k specialized block builders, then if every proposer is following the strategy we just discussed, for every pair of proposers I and j, the expected reward for proposer I is going to be at most a 1 plus O of 1 over log k times the rewards that j earned. And this will be basically the rewards they earned if they were ended up being chosen to be the leader for a slot. And so we can see, if k is reasonably high, that this really lets us bound kind of the maximum difference in rewards different proposers earn, even if they have different levels of sophistication at still building blocks. And so in conclusion, we started by seeing that kind of without PBS in a world where validators are both building blocks and participating in consensus, that there are strong centralizing forces from block building that could threaten to centralize the validator set. However, with PBS and sufficiently high builder competition, validators receive approximately equal rewards, and this can really relieve centralizing forces on the validator set. In terms of future work, one main thing we don't address is that block builder centralization can still be a problem in this setting. Even if the validator set is very centralized, we might expect, and even as we see in practice, that there's not a ton of different block builders. And so there's still open questions around how we can introduce new mechanisms to improve builder decentralization while still kind of relieving centralizing forces from the validator set. And so, there's been things like inclusion lists that have been proposed that can maybe also just lessen the effects of what builder centralization might threaten. And so there's open questions on how new mechanisms like this can emerge and how it might interact with PBS. And just finally, disclosures. None of this talk is the views of A16Z. It's just the views of me and my co-authors, and nothing that's been discussed should be taken as investment advice. Thank you.